Good morning or good evening or wherever it is you're viewing this. It's going to be a quick one. I just want to introduce you or illustrate some ideas about basis functions. I know there's a fair bit of reading this week that discusses basis functions, but it can seem abstract. I think once you take a look at this video, you'll be able to understand where the pieces come together and that it's really not as complicated as Kagan Holthausen or Zabel and Aslam seem to make it. So let me share my screen, and it goes like this. So you should be able to see my screen here, and I am going to slideshow it. We're going to play from the start, and it's a real quick one. It's just on basis functions. So here's the take-home messages that I'm going to want you to glean from what we do here. I want you to see the difference between Slater and Gaussian functions, and it's significant. I want you to understand what contracted Gaussian functions are. That is, they're grouped together in a fixed linear combination and varied as a single function, even though it's composed of several Gaussian primitive basis functions. And then I want you to see what polarization functions do. You'll have opportunities to apply all of these types of basis functions in the calculations you do, but this will give you some sense of why it might be the specific basis functions behave differently. All right, so that's it for this. Let's take a look at this. So I created this in Mathematica, and if anybody likes Mathematica and wants to play around with it, I'm happy to give it to you. But for our purposes, all you really need is these PDFs, and I'll remind you that the PDFs or PowerPoint presentations associated with any given video are on the Google Drive associated with the videos for that week. So the first thing I want to introduce you to are single Slater or Gaussian functions. And so they're named here. Here's Slater, and it's going to just depend on x. For the moment, we're only going to plot it in one dimension. And it is an exponential, a decaying exponential in x. And so since we're in one dimension, x goes from minus infinity to plus infinity. If we were in 3 dimensions, we'd put an r in here. We wouldn't have to take the absolute value. But all you want to think about this is an exponential that is biggest at the origin and decays, surprisingly, exponentially as it goes along. And here is that. I've color-coded. Here's blue Slater. This is what what an exponential function looks like. And as a cusp at the nucleus, that is, it does not have a well-defined derivative at the nucleus. And it decays, not much to say, exponentially away from the nucleus. On the other hand, a Gaussian in x goes as e to the minus some coefficient I've called alpha here, x squared. So this is going to decay more rapidly, the Gaussian function will, as a function of distance away from the nucleus, because once you get to 1, x squared is bigger than x. And so it decays quite rapidly here. The other difference you see is that there's definitely there's zero derivative of this function at the nucleus. It's well defined. And so the two things that you want to take home about the difference between Slaters and Gaussians are, one is they have a different functional form. One goes as e to the minus x. It goes as e to the minus alpha x squared. But the other piece is one has a cusp, one doesn't at the nucleus. And the Gaussian decays more rapidly. We know that for hydrogen and hydrogenic orbitals, they do decay purely exponentially, and the decay constant has to do with the square root of the energy. They decay purely exponentially as you move away from the nucleus. So in a real sense, actually no qualification, the Slater is right when it comes to hydrogen, and the Gaussian is wrong. The Gaussian function, if you called that the wave function, would give you a higher energy based on a variational principle than the Slater function would if you choose the coefficients in sort of a balanced way. I'm sorry, the exponents in a balanced way. Okay, that Gaussian stinks for hydrogen, but what if we said, I'm going to take 3 different Gaussian functions, and they're going to have different exponents. Remember that here's the Gaussian, I defined it with alpha. So if I make alpha bigger, then at any x squared value, that makes alpha x squared bigger. And that means that that Gaussian should be smaller at a given x value, the bigger alpha gets. So I'm going to pick three. One that has a really small alpha, one that has a medium-sized alpha, and one that has a big alpha. So it's like Goldilocks and the Three Bears, right? This one's too big, this one's too small, this one just right, I don't know. But in any event, the alpha here is going to give us a function that is narrowly peaked at the nucleus. And this function here with the 0.1098 alpha is going to give us a really diffuse function. And then alpha 2 gives us a function that is somewhere between. And I have picked, based on a nonlinear least squares, to a Slater function that's appropriate for hydrogen. I've picked coefficients for each one of these. So there's an exponent for alpha 1, alpha 2, alpha 3, and there's a coefficient. And the way the function is constructed is I take the coefficient and I multiply it by the Gaussian function with alpha 1, and then add to that the Gaussian function for alpha 2 with its coefficient, and the Gaussian function for alpha 3 with its coefficient. And you can see it right here. It is a sum of 1, 2, 3 Gaussians. And so we get an energy, we're going to get a function that is a linear combination of those three Gaussians. Here's what it looks like. By golly, look at that. There's the Slater function. I'm sorry, let's make sure I think my colors change. No, that's right. There's the Slater function, and it definitely has a cusp at the nucleus. Here's the contracted Gaussian, the sum of three. And it doesn't have a cusp, but it's got more of a peak than the previous Gaussian did. And look at how well it represents the decay of that exponential. Even though none of those single Gaussians can do that by themselves, the sum does a pretty good job. Now, if I could plot this a little more carefully out here, you'd see that there really were differences, but they're in a tail. There's almost no electron density there. And more interestingly, Gaussians in one dimension and in three dimension are complete. That means, in principle, I could write any function that is continuous and differentiable using the Gaussians and decays to zero at plus or minus infinity. I could use the Gaussians to do that. So, if I had more Gaussians, I could really mimic this Slater function. Now we go a step further. Here is the so-called double zeta 6-31G basis for hydrogen. So the way the nomenclature works here is the core would have a contracted function of 6 Gaussians, but there is no core for hydrogen. The valence space has a 3-function contraction and a 1-function primitive function. So here they are. There's coefficient 1, and you see when I do this 6-31G, I even have a bigger alpha for one of my contracted Gaussians. Here's the second, here's the third, and then there's a 4th alpha that's relatively diffuse. And so the contracted function, the 3-term contraction function in this 6-31G basis looks like this. And then we add to it Gaussian 1. Well, we haven't added it to it yet, excuse me. But what we have done is here's the original Slater function. Here is the primitive function that's diffuse. And here is the 3-term contraction in the 6-31G basis. And you see, it peaks pretty well at the nucleus. The optimal mixing for these is, in fact, I picked 0.9 here. The optimal mixing is 0.75. And you can see that when I pick 0.9 as the mixing, the way this works is when I pick 0.9 for the mixing, the larger coefficient is that of the single-term Gaussian. And when I do that, my now 4-term Gaussian doesn't peak as much at the nucleus. On the other hand, it decays more slowly than the exponential out here. Now, we'd let the variational principle tell us what the optimal mixing was. And if I put 0.75 here, it would look pretty much like that Slater function. Okay, so that's contracted basis functions. Now I have to shrink this guy, get rid of it, in fact. Instead, I want to turn to polarization functions. So here, as you remember from your reading, what you're doing is you're adding higher angular momenta So if your occupied orbital was an S, you'll add a P function. If your highest occupied orbital was a P function, you'd add D functions, and so on. And what I want to show you is how mixing two different angular momenta allows for shape changes in orbitals. So here what I've done is I've created a 1s orbital. So this is now in 3 dimensions. It's e to the minus r squared, divided by some normalization constant. And here's a P function. It is z times an e to the minus alpha r. And here's a D function. It's z times x e to the minus alpha r. Right? So I'm just going to plot the 1s function right there. And that's what it looks like. It is symmetrical about the z-axis. So it's equals 0 as a peak, and you go plus z and minus z. You get decay exponentially. Here's a contour plot of the 1s function. So instead of just plotting in one direction, I'm really looking at the values of the functions in a plane. And what I'm going to do is calculate all the values, and then I'm going to connect the dots of all that are equal. So you should think about this as a topographical map. The way this is color-coded is blue is essentially 0, and the higher the value of the function, the more yellow it is. And I stopped with this contour right here. But the point is, the function is going up, 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 up as you go closer to the nucleus, and it'll finally get to a peak there, and then as you leave the nucleus, it goes down, 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 down. So there's that sense in which this is exactly sort of stacked on top of one another, increasing function. But it's just a way to represent the function. Functional values change as a function of distance. Now, I'm going to do the same thing for the 2p function. Here it is, and I'm going to plot along the z-axis. And so if it's a pz function, it's positive on the plus z, it's negative on the minus z. But a contour plot of that would look like this. So I'm coming in along the plus z-axis, and it gets bigger and bigger and bigger, and it gets maximum, and it starts to go down, down, down as it crosses a node. Then it changes sign. It's going negative, negative, negative. It's most negative here, and it comes out. Or I could turn that on its side, and I could plot it along the y-axis, and it would look like this, and we're going to use that in a second. The 3D function that I've chosen, the xz, on the z-axis is exactly 0, so kind of boring there, but there's a contour plot of it. You see plus, minus, minus, plus. It looks like a D function with which you're all familiar. So now what I'm going to do is I'm going to add a little bit of P function to an S function. And I want you to think about what that would do. I'm going to pick this pz function here. I'm going to add it to this S function. This S function is everywhere positive. I'm going to add a little bit of a function that's positive here and negative here. What do you think it ought to look like? Well, if you have the PDF open, you already know. But if you don't, if you were able to practice delayed gratification, then you say, okay, I got a lot of S and a little bit of P here. What happens? Well, in one dimension, well, the function increased relative to what it was just as an S function here, because you added some positive P value. But then here, negative, well, that's because you added some negative P on that side. Or in a contour plot, it looks like this. It is pooched, if you will, in one direction. It sticks out in one direction. And that's a function. The extent of poochedness is a function of how much P you added there. But you see, I changed it from a cylindrically symmetrical function to something that is biased towards one direction. We can play the same thing with P functions. If I took the py function I had above, there, and I added this D function to it, what would you get? Well, if you didn't cheat, thought about it, you'd know that what you got was something like this. You bent the P orbital a little bit, you polarized it, you made it bend towards the right side. Now, why might that make sense? Well, I had a P orbital here with a single electron in it, I brought up a plus charge. There's no good reason for it to be symmetrical about this atom. It should bend a little bit. And that's part of what we try and account for with these polarization functions and basis sets. Now, I know it seems kludgy, right? Oh, he added a little P, a little. We let the variational principle tell us how much to add. So in that regard, it's It's unbiased, I should say. It's not, I just want to create an elephant-looking function. So that's my take on basis functions. Happy to discuss it with folks ad nauseum, as you will find out, but I'm going to stop here and put this up.